He knows a lot about the science stuff, Professor Dave explains.
In the previous tutorial, we introduced the wave function, which is represented by the Greek letter psi. We talked about how to apply operators to the wave function, but we didn't talk much about the wave function itself. So in this tutorial, let's try to understand the wave function a bit better. We should note that much of this discussion will assume a working comprehension of concepts in linear algebra, such as vector spaces. So if your goal is a deep comprehension of quantum mechanics, my linear algebra tutorials are available should you need some review. If you're up to speed, then we can begin to unpack a few things. The best way to go about understanding the wave function is to describe what it does. If we consider some quantum system, it can be described by a set of wave functions, and the wave functions which describe that particular system can be said to form something called a Hilbert space. A Hilbert space is a particular kind of vector space. Hilbert spaces have some specific rules and properties that we won't fully explain here. For now, let's just talk about how to imagine the wave functions that form them. We can picture wave functions as vectors living in a vector space of potentially infinite dimensions. So for comparison, in a three-dimensional vector space, we have the Cartesian components, x, y, and z, forming a basis for the vector space. They are orthogonal, so their linear projections, or dot products, are always 0. That is, the dot product of x and y is 0, and the same goes for x and z, as well as y and z. But the dot product of x and x is not 0, nor is it for y and y, or z and z. These basis vectors are linearly independent, so we can't write any of them in terms of the others, since no combination of x and y can give us the z vector, and so forth. Now back to wave functions. Each wave function is a vector in a Hilbert space, just like x, y, or z are vectors in your everyday Cartesian space. Everything we just said about x, y, and z can be applied to the set of wave functions that comprise that Hilbert space. The difference is that a quantum system may be described by a large number of wave functions, much more than 3, all of which are orthogonal with each other, and they are also linearly independent, meaning that none of them can be written in terms of the others, just like in the three-dimensional case. Now that we are conceiving of wave functions as vectors, it's time to introduce some new notation, Bra-Ket notation. This notation utilizes two constructs, bras and kets. These use angle brackets and vertical lines to represent certain vectors, and we will use this notation with the wave function. When we use a ket this way, we are referring to the wave function in vector form, where a, b, and c can be considered coefficients that accompany each component of that wave function, no different from how we've used vectors to represent functions in linear algebra. So psi equals a psi 1 plus b psi 2 plus c psi 3, with each of these representing basis vectors. This represents the sets of linearly independent wave functions that are solutions of the system. So once again, considering the ket to be a shorthand for the vector representation of this wave function, the bra can be considered the complex conjugate of the ket, or psi star, which is the transposed conjugate of this vector, therefore involving a, b, and c arranged in a row instead of a column, and with a star, indicating that each term is the complex conjugate of its corresponding term in the ket, or a star, b star, c star. Now we are ready to define a new operation called the inner product in a Hilbert space, which uses the Bra-Ket notation we just learned. The inner product of psi 1 and psi 2 is equal to the integral over all space of psi 1 star times psi 2 with respect to x. A few things to know regarding the inner product are as follows. The inner product of a wave function with itself is always 1, and the inner product of a wave function with a different wave function that is not a linear combination of the first is always 0. This makes sense if we think of the inner product as the projection of one vector onto another. Any orthogonal projection is zero since we are dealing with linearly independent vectors, like how this unit vector in x does not contain any amount of the y or z vectors. But any projection of a vector onto itself must be 1, as a vector is equal to itself. The way to represent these relationships at the same time mathematically is to show the inner product of psi n and psi m as being equal to something called the Kronecker delta, which is presumed to be 0 when n and m are unequal, and 1 when n and m are equal. Let us reiterate that for a Hilbert space, the inner product is equivalent to the dot product, and inner products give a scalar as the result of the combination of two vectors from a vector space. So we can pretty much think of the inner product as the dot product for wave functions. The way we are using the dot product in this context is indeed the same as what we are familiar with, even though we are using integrals and functions rather than sums and vectors. It is simply that wave functions within a Hilbert space don't correlate with physical reality. Ket of psi is a vector in the Hilbert space, while psi of x is the projection of that vector onto the space we are familiar with, such that we can describe observables like position and momentum. With an enhanced view of the wave function, let's now return to the concept of the probability density function that we introduced in the previous tutorial. First, let's recall the mathematical meaning of the probability density function with the following equation, involving the product of the wave function and its complex conjugate, represented by psi star. So p of x equals psi star times psi, which equals the absolute value of psi of x squared. Now let's expand a bit. The probability density function tells us that at some instant t, the probability p of finding a particle between x and x plus dx is equal to psi star times psi. We should note that the probability density is always a real number. To find the probability that a particle will be found in some region of space, we can calculate the following integral of the probability density function from x0 to x1. Then let's understand that if we integrate the probability density function from negative infinity to positive infinity, this will equal 1, meaning that the probability of finding the particle somewhere in space is 100%. If we were applying this to a classical particle, we would get a very narrow peak centered in a specific location, like x equals 5. Integrating only from 4 to 6, we would still get a result of 1, since the particle is located within these boundaries. If we were to integrate over some other interval, we would get a result of 0, which makes sense, since the particle is not there, but is somewhere else. But with a quantum particle, we get a different result. Perhaps it is still located at x equals 5, but its presence is much more diffuse. In this example, the probability density function extends like a bell curve, let's say from 1 to 9. Integrating from 4 to 6 will no longer give us 1. We will get some fraction of 1, as will be the case with any other interval that contains some of the probability density function. Integrating over this interval will give us something close to 1, let's say 0.93, but there is still some probability when performing a measurement of finding the particle towards either edge of this bell curve. This is why normalization is so important. It ensures a result of 1, which is the equivalent of knowing with certainty that the particle is located within a particular interval, because it's the largest possible interval, all space. It tells us that this particle exists, even though we don't know exactly where. Now we need to introduce some more terminology. We can say that wave functions, which are eigenfunctions of observables with physical meaning, are normalized. Again, by normalized, we mean that if we calculate the integral of the probability density function over all space, which as we know is the integral over all space of the modulus squared of the wave function, it will always be precisely 1. Rather predictably, two examples of observables with physical meaning that will have eigenfunctions in the form of normalized wave functions are position x and momentum p. In the next tutorial, we will look at the inner product of psi and another wave function of the same vector space, like psi1, psi2, and so forth, which correspond to different eigenenergies of a quantum particle, and this will be equal to 0 due to the linear independence of all wave functions forming such a vector space. But first, let's continue to discuss normalization. It is the case that the Schrödinger equation is linear, which means that in finding a solution for this equation, if we arrive at a wave function phi1 that doesn't satisfy the normalization condition, that is, the inner product of the wave function with itself does not equal 1, but rather equals some constant c that is not equal to 1, then we need to normalize it. We need to find a way to make c equal to 1. Now, it is the case that if a wave function is a solution to the Schrödinger equation, then any linear combination of this wave function will also be a solution. So given that phi1 is a solution, then phi2, which is defined as equal to a phi1, must also be a solution. So since the inner product of phi2 with itself would look like this, we can also just replace phi2 with a phi1, and we can then pull the constants a star times a out of the integral. This will equal 1 because we have decided that it should equal 1, because we need a normalized wave function, and that is the condition of normalization. Now we can find what a must be for this to be true. So recall that the expression for phi1 gave us a value of c. Let's therefore replace this entire integral in the previous expression with c, since they are equivalent. That gives us a star times c equals 1. Recalling that a star times a equals the absolute value of a quantity squared, since these terms differ only in the sign of their imaginary terms, we can then divide both sides by c, take the square root, and a will be equal to 1 over root c, where c represents the inner product of phi1 with itself. The main thing we should take from all this is that all wave functions with physical implications must be normalized. In other words, the definition of the probability density function implies that wave functions which are solutions of the Schrödinger equation must be normalized, and we will talk more about the Schrödinger equation in the next tutorial. Now that we have a better understanding of wave functions, let's see what we can do with them. First, let's talk about the superposition principle. This states that quantum systems can be described by combinations or superpositions of wave functions, which still must satisfy the normalization condition. One example of this is the famous double-slit experiment, which we introduced on a conceptual level in a previous tutorial. Now let's add some math. As we recall, given this grating with two slits, a quantum particle will exhibit wave-like behavior, passing through both slits, and generating an interference pattern at the detector beyond. The interesting feature of this experiment is the act of the particle passing through both slits simultaneously, and at that precise moment, we can describe the quantum state of the particle as the superposition of the particle being in the left slit and the particle being in the right slit. Mathematically, we would represent this as psi equals phi L plus phi R, essentially representing the sum of a wave function localized at one slit and a wave function localized at the other. Now let's introduce two constants, AL and AR, which represent the probabilities of the particle being at either slit. If we desired, we could make this more complicated by adding more slits, and in turn, we would simply add more wave functions to this equation, each with their own respective constant. If there were 4 slits, we would describe the superposition this way, with 4 wave functions and 4 constants, where phi1 represents the wave function of a particle at slit 1, and a1 represents the probability of the particle being found at slit 1, and the same for the other 3. What we must wrap our heads around as best we can is that the superposition tells us that a particle can be at several points at the same time, and this is precisely what the double-slit experiment demonstrates, as the particles do physically pass through both slits. It is a probabilistic way of viewing reality that is difficult for our classically trained brains to comprehend, but nevertheless, this is how the universe operates on this scale. Now that we understand normalization and the probabilistic interpretation of quantum mechanics, we are ready to develop one of the most important topics in quantum mechanics, and that is the calculation of expectation values. Earlier we saw that the integral over all space of the probability density function gives us a value of 1 for a normalized wave function. This 1, which is the maximum value possible, tells us that the probability of finding the particle somewhere in space is 100%, which makes sense since the particle has to exist somewhere. Now, if we want to determine where it is most likely to find the particle, we have to perform a similar calculation. Given that we are talking about the location of the particle, we are describing its position, so we will need to use the position operator in conjunction with the probability density function. The operator will be placed like so, in between psi star and psi, such that it acts on psi, and this expression will be equal to x0. x0 is an expectation value. It is a number, which in this case tells us the most probable location of the particle. Now let's try to understand this in greater detail. In statistics, an expectation value is a weighted average of a variable. Think of it this way. You want to measure the variable x, but it does not have a definite value. It exists as a distribution of values, something which will be true all the time in quantum mechanics, as we are beginning to understand. The expectation value is the weighted sum of all possible values that x can take times their respective probabilities. So each value contributes to the sum in a way that is proportional to its respective probability. Now let's apply this to quantum mechanics. Say we are performing an experiment many times. Perhaps we are throwing a quantum particle out the window, such that it lands on the ground below, and we take a picture of where it lands each time. Then say we superimpose all of the pictures for all the trials, so that we can see all of the final positions at once. And whenever it lands in the same spot again, that spot becomes darker. This singular image tells us the most probable position for the particle, with the darkness of each spot relating to how that spot is weighted. And we can consider the darkest spot to be representative of the expectation value for position at the measuring device, which in this case we are analogizing to be the ground itself. Once again, mathematically, we will write this as the integral over all space of psi star times the position operator acting on psi. This is how we define the expectation value of the x-coordinate at a given time t, which is written this way and read as the expectation value of x with wave function psi. Notice how we use both left and right brackets with the variable in the middle. We can write an equivalent equation for the momentum operator, whereby the expectation value of p equals the integral over all space of psi conjugate times the operator p acting on psi. We can then rewrite this using the definition of the momentum operator, which, as we recall from the previous tutorial, is negative I times h bar times the partial derivative with respect to x. This applies in a broader context as well. We can write all dynamical variables as functions of position and momentum. This means that it is possible to find the expectation value of any dynamical variable q by calculating it this way, with the expectation value of q of x and p being equal to this expression. Let's apply this to one specific example, kinetic energy. In the classical physics series, we learned that the kinetic energy of an object, which from now on we will represent as t, is equal to 1/2 mv squared. And since momentum equals mass times velocity, if we just put an additional mass term in both the numerator and denominator to keep the expression equivalent, we can change m squared v squared into mv quantity squared or p squared, leaving us with p squared over 2m. Now we can take this classical equation and translate it into a quantum equation by replacing momentum with the momentum operator. Let's then plug in our expression for the momentum operator, putting it out front, but twice, since the operator is squared. Now to simplify, negative I times negative I gives I squared, or negative 1. So let's just get rid of those and make the whole expression negative. Then we can pull h bar squared up here, and the partial derivatives multiply to give the second derivative with respect to x. This is the quantum operator for kinetic energy, which we will be using frequently. Now let's find the expectation value for kinetic energy for a given wave function psi. As we learned, to do this, we place the operator t in between the bra of psi and ket of psi. We can then replace the operator with the expression it represents. We get the integral of psi star times the kinetic energy operator acting on psi dx. Recall that even though we are not writing it explicitly, psi depends on x, which is why we are able to differentiate it with respect to x. Now recognize that we have some constants with h bar and mass, so let's pull all of this out of the integral. That leaves psi star times the second derivative of psi with respect to x dx. So we can now calculate the kinetic energy of a quantum particle given its wave function. In this tutorial, we did several things. First, we more clearly defined what a wave function is from both a conceptual and mathematical standpoint. We learned that wave functions are a special type of vector living in something called a Hilbert space. Next, we outlined the most important properties of wave functions, namely that a quantum system is described by a set of wave functions that are linearly independent, meaning that their inner products are zero, except for their self-inner product. Then we stated that a wave function consistent with physical reality must be normalizable, meaning that its inner product with itself must be equal to 1. From here, we must simply know that for any wave function that is a solution to the Schrödinger equation, it is possible to normalize it. We will expand on this in the next tutorial. And finally, we learned how to use wave functions to perform one of the most important calculations in quantum mechanics, and that is determining expectation values. We learned what these are, and then calculated expectation values for position, momentum, and kinetic energy. That's a lot to take in, so watch once more from the top if you need to. Otherwise, let's move on to a deeper examination of the Schrödinger equation, where many of these concepts will be further clarified through example.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.